or yeah, you got. That thing's not going to catch on fire.
No. Spoken like a true safety.
That's right.
All right, thanks for coming this afternoon. Our next presentation is by Sean Stapf. Sean currently owns and operates SECorp, which is a small consulting company performing physics analysis. Sean's also employed as a civilian engineer for the Air Force, supporting issues of range safety for rocket launches at Cape Canaveral and Kennedy Space Center. Prior to these two efforts, Sean was employed for 14 years as a civilian engineer for the Navy, performing physics calculations on rockets, ejection seats, weapons, aircraft, explosive ordnance disposal equipment, and various other energetic devices. Today he's going to talk about things. And I'm proud to say I've known Sean for several years. He's one of the most easy to understand engineers for somebody like me with a management degree. It's great to be able to sit down with him and understand things and talk about real physics and engineering. And he can put it in terms that even somebody like me can understand. So please join me in welcoming Sean Stapf.
Thank you, Ted. I can speak it simply because that's the only way I can understand it. So you're hearing right what is going on in my head. I have to do one disclaimer. As he mentioned, I'm currently an engineer for the Air Force and prior engineer for the Navy, but I'm not representing any U.S. government positions as I speak here. I am reflecting no Department of Defense information. That is privy only to my job and similar disclaimers like that. You get the idea. I'm just a guy here. So I know a lot of you guys have, you know, what we call even in the industry, we call you guys the real rocketeers, the ones that you're building stuff on your own, you're tinkering with new ideas, you know, how you might even cast your own propellant, you're assembling multi-stage rockets sometimes, and you're kind of free of the bureaucracy of it. That may mean some of you have blown off a couple fingers, but you might have knocked out a window of your garage, but you're kind of on the leading edge, really. So this will be a window into what you might have to go through if you did have to answer to somebody other than your wife or husband when they say, "What was that explosion out there?" So let's say that somebody came along with $1 million for one rocket launch. Hey, that's probably the best deal you've had pitched at you for most of the rockets you've launched. And they're going to give you a year to do it. That sounds like a great deal. The only catch is that before that launch, you have to fully analyze it. You have to have done a full pre-flight analysis. So that's we'll go over some of the topics that you might end up having to go through. And just in case people were falling asleep, I had some background music. It's also the there's more music on the right channel. This is just left channel. Anyway, all right. But so we'll go over some structural, thermal, the trajectory, computational fluid dynamics, and all the effects that those have on you. When you go to calculate what's going to happen on launch day, there's a lot of the little features that might cause you the problems when the rocket goes up. You know, you've gathered your family, you've got 20 people there, that maybe some guys have helped work with you on it. What went wrong? So that's what we're going to be able to talk about here. This is a little hard to see. This is a grainy image of one Apache helicopter escorting another Apache helicopter. The Apache helicopter has two launch pylons on the starboard, and you'll see, so one rocket hit the dirt. So, well, actually both rockets, of course, hit the dirt. One of them fell short of the target. So you see one puff down here, and you see another puff in the distance there. So what we're looking at is with the Apache, you can see they were both fired simultaneously. You've got a port launcher and a starboard launcher. Both are 9-tube launchers. They're mounted on the Apache pylon, which can articulate up and down, but the two rockets really should have landed together, maybe 40 feet apart. But because the pylon can't aim individual pods, you can aim up or down, but both launchers together. So we know we should have had two spots in the dirt out there, and instead one arced straight down or rapidly down and hit the dirt there. So you've got an answer for that. In your case, when you launch a rocket and you see it arcs over your family and friends that have just come to watch it, you've got an answer for why did that thing turn. Could it be inside your nozzle? You've got maybe some fancy contours in the nozzle throat. Maybe you've got some fins on it. These are fancy pop-out fins. You probably built a nice launcher, some sort of fancy mechanism that's going to guide your rocket. Was it some sort of mechanical interaction with that? Was it something internal to the rocket? The propellant burned through the liner and maybe started leaking some gas out the backside of where the nozzle connects to your main motor case. So you got some lateral thrust. Did that steer you down? It's a big fault tree. So to really do the fancy analysis, there's a lot of parameters that you can look at. One is, of course, structural analysis. What held together, what didn't. Dynamics is how these parts accelerate, just force equals mass times acceleration. Mechanics is some of the interaction of the kinematic parts. And the trajectory analysis, of course, is what you're really interested in. Some fluid dynamics. Now with modern computers, you can run a lot more than you could, 10 years ago you had to have a whole room full of computers just to calculate how the air might flow around the fins and the nose. And also the CFD, computational fluid dynamics, for the inside of the rocket too, where you can also report some of the thermal soak through the nozzle parts and get some of the interior ballistic. All of that can boil down into whether you did a safe launch or not. You've got 20 family members that came to watch this rocket that you've been working on for months, and it arcs over them. Then you kind of can think in your mind, well, is it safe or not? If it hurts somebody, that's a really bad day, but maybe it's very unlikely. But if it's a likely event and it's a really bad day, you're in the red zone there. So. And then finally, you can get some statistics, and that's what my better half over there is going to present on for the next presentation in the flamingo artichoke blue.
The long neck.
The egret room, thank you. So even if you get a normal launch, a nominal launch, everything, you sit back and say, wow, that went just the way I meant it to go. That parachute, when it brings down your payload, is not going to land exactly the same place if you launch the rocket again in a few minutes. If you do 10 launches, you're not always going to land that parachute in the same spot. So some of the statistical variation of even the nominal launches is one of the things that we can talk about. I know Pat wants to get his boombox back into his pickup truck there, I think. You want me to pull this right here? All right. Woo. Wow, the dilithium crystals are cooling down. That's all right. So we got another presentation around the corner where they're going to be talking some awesome stuff. Yes, sir. Thanks again, Pat. Next year we're going to have
downtown. Next year we'll have 2.
Yep. All right. So. We'll get into it here. So first off, dynamics. You've got a rocket launcher. When you're launching from, say, a nice field in the town where you live, your launcher is probably holding still. But sometimes the launcher is going to be on a helicopter and it's vibrating, and the flexure of the strut is also kind of undulating. And then you've got dimensional slop in between the rocket and its launch tube, and all of that's going along together. So when you hit the fire button, you're not exactly sure where your rocket's pointed. Another thing you can do with analysis, simply force equals mass times acceleration is really all you need, and generally that's almost all you need anywhere. But the fancier your software gets, you can handle 200 parts calculated simultaneously, and you can get the rotations of those parts. So you can see, in this case, you may have a catastrophic failure. Your rocket comes up, and your thrust was misaligned, so it starts swirling around, and then that breaks or stresses some of your motor case, so that rips open and busts the propellant drain, releases all the debris and the gases. Then that debris field comes down. You may have told everybody, hey, you're good if you just stand right here, but then you can really track a few pieces. You're going to have to tell people to keep their baseball gloves in the air for just a few more seconds. So what made that break apart? And when it breaks apart, what made it go left or what made it go right? How far to the left might it go? Well, that really can get down into, it's still force equals mass times acceleration, but the forces are now from mechanical parts. So inside your rocket, you may have a two-stage rocket. First stage and second stage are mated together, and they're trying to struggle with each other as they ascend. And then you may have put a payload up there. You've got either maybe a parachute pack or some other device that's going to come out. Those are under G loads. Those are rattling around. You want your nose cone to come out. Those are interacting parts. And all of those are under a dynamic load. So it's good if you're able to calculate how the interfaces, every mechanical piece that you expect to touch one another and then not touch one another and then touch one another again, those are parts that need to be analyzed. But when these parts touch, they aren't, of course, rigid parts. There's no such thing as a rigid part. Every part is flexing. When you put a load on it, it's bending slightly. So it's good if you can do the finite element structural analysis that tells you how much your nose cone is flexing, maybe how much your fins are flexing. And recall that these parts don't just flex when you're pressing on them, they also oscillate under their own natural frequency, just like a guitar string. You can strum it once and it'll continue vibrating under its own preference. And so with finite element analysis, you can not only calculate the stress as your nose cones or the interstage between your first stage and second stage. As those loads are bending parts, you can also capture some of the vibration as the parts respond. Well, and then when you first thought, okay, I've finally analyzed all the hardware and all the dynamics, recall that everything you did was at 75 degrees. We'll say you were working on this in the garage, or you were working on it in the laboratory. Maybe it's middle of the winter and you've got a heated garage. So you assembled stage one, you inserted the propellant drain cartridge, you assembled the nozzle, you interfaced stage two, stage one, and you put on the nozzle, the forebody or the nose cone. All of that was at 75 degrees. You're excited Saturday, you're going to get all your friends to come out. We're going to do a 10 o'clock launch and it's 40 degrees that morning. So you've got this rocket, you put it in the back of the pickup truck, everybody's heading out for a great launch. All of a sudden, the rocket goes up, but the nose cone doesn't come out, or the stage one doesn't release from stage two. Well, the rocket was 40 degrees, and you assembled it at 75 degrees. So everything's shrunk, and if you have dissimilar metals or materials, some parts may shrink more than others. So that's some of the thermal analysis can calculate how things will change just environmentally. Don't forget, though, you've also got thousands of degrees on the exhaust gas. It's raging through the nozzle, and you've probably got a very tough material for the nozzle throat, but that's inserted inside another layer, which is inside another layer. So as the heat soaks through your nozzle during the burn, you may crack parts, you may stress parts, they may swell more than you had anticipated. And not to mention, after that, the exhaust comes out the back and it radiates heat. So just like being around a campfire, if you put your hands towards the campfire, you feel the warmth coming up. So that means all of the other rocket parts are feeling some of the heat. The space shuttle and everything back to Apollo and everything in the future, you can look at the rear end of these machines, the space shuttle. A lot of the insulation is on the back end of the entire stack. Why do you insulate the back end? The front end is what's driving through the aerothermal heat on the front end, on the nose, right? Why would you insulate the back end? That's because your blazing hot gases are coming out here, and it's like a campfire. It's warming everything on the aft end of the rocket. So that's thermal, but now you know what's hot and what's cold. Well, that's thermal structural analysis. Things warp when they get hot. So how much did the diameter change? Maybe your fins are fluttering. Some of your rockets hit Mach 2, some even Mach 3. When you get to those speeds, you've got this thin little fin on your rocket that's trying to drive through the air, and it's actually warming up. So not only would, say, aluminum loses half its strength by the time you get to 200 degrees, but it can also be warping and twisting around depending on how you've assembled it. So thermal structural analysis tells you some of this warping. And then finally, you get to the computational fluid dynamics, where internal to your rocket, you've got all this chaos going on. Or I shouldn't call it chaos. You've got a lot of order going on, but it's a lot of energy, a lot of dramatic things are happening in a small space. So going from 0 to Mach 1 to Mach 3 as you get out the nozzle, your exhaust concentration is going from ambient to saturated. You've got, of course, temperature and pressures building up all at the nozzle throat. So all the loads, the pressures, the thermal, pressure and thermal loads that are going on there are good to fully analyze in your pre-flight analysis. And then finally, of course, you know, if you've got a 2-stage rocket, you might want to put some fins on your top stage, right? Isn't that great? Because you want to drop the first stage off and still stay stable. Well, now you've got fins on the front end of a rocket. That's a bad idea. That's the way you make a rocket flip around and fly backwards, right? So you're trying to put, as you try to put different sized fins on your aft end and your midsections and still maintain that you're stable, there are, as you know, different degrees of stability. You can handle a third of a degree thrust misalignment if you have 4 calibers of stability. You can handle maybe half a degree of thrust misalignment if you've got 6 calibers of stability. Those all can be calculated with CFD. I know there's a lot of hand calculations. I personally do hand calculations more than I would do CFD. But just if somebody's going to pay you $1 million and spend a year on it, they're going to want you to have a pretty picture of it. So that's about it. We can go back to any slides if you have any questions. But that's kind of hitting on the topics of thought here. What do you got?
How much would you have left over to actually build the rocket?
Very good point. Yeah, $1 million sounded really good at first, didn't it? It's like, wow, what am I going to do with the other 990,000? But after we've gone through this, now a year looks pretty short, and $1 million looks pretty thin. So. Yeah, so that's of course the competition. As you see, Lockheed and Boeing, they're all trying to put, SpaceX, they're all trying to put rockets on the pad and make money. They would, love to be able to calculate every little nut and bolt to the nth degree. Then they have no profit and they won't be putting a rocket up. So, yeah.
What kind of software were you using?
Gotcha. It's a mixture. For the solid CAD, structural thermal and thermal finite element analysis, I'm using SolidWorks. And then, of course, got the modules that you can buy to do the structural and thermal. I'm also using Flow in SolidWorks for CFD. It's the Flow EFD engine, which is used by ProEngineer and CATIA and SolidWorks. So they all have the different GUIs on the front, but you're actually using an engine, the CFD engine, that's the most common out there. For the 6 degree of freedom analysis, SolidWorks actually does have the same solver available, but it's not as good to interface with. So on the mechanics, that is Atom software, and Trajectory is Atom software. That one is the kind of the industry standard. In the late '80s, they came out, and it was up mostly in the big car industry up in Detroit. They would calculate how all the wheels and the gears moved, but then it picked up, and by the '90s, it was the 6 degree of freedom industry standard across Air Force, Navy, NASA, Boeing, and all the big guys. Yeah.
So a lot of these softwares are sort of expensive. Is there any sort of open source analogies to this that people who don't have as much money for licenses could use?
Exactly. Good question. Yeah, I mean, I probably Google it once a year. Here's all the professional software. Isn't there a freeware out there that calculates force equals mass times acceleration? There is a 6 degree of freedom code that I've seen maybe 5 years ago. I can't even remember the name of it. But certainly there are structural and thermal finite element codes as well. And now there's even a few CFD codes. And all of them can do basically like 1 part, maybe 2 parts that are moving, and they may run a little slower. But the main drawback is just the menus. It's a shame to say, but just the user friendliness of it. The big money put all their work into the GUI, the graphical interface of how to put in that this is a red object for stage 1 and a yellow object for stage 2, and it has this thrust oriented in this long axis, so if it tilts this way, the thrust tracks, but the aerodynamics are going on perpendicular to the cylinder. All those interfaces can get complicated, and when you get the freeway right now, they don't have as good an interface to keep the order and all that. So it's kind of a lot like when you buy PowerPoint or Excel, it's such a refined, menu-driven point and click that makes it smooth. There are probably other ways. You can get free database and free presentation software, but they just won't have all the nice buzzers and whistles. But the engines, the actual calculation that's going on in the background, none of that has changed for 20 years. Everybody's just working on the menus to get to those engines. So kind of a shame there that it's not free yet. Or maybe it's good, because if ever free to everybody, then I would be out of work. Yeah. All right. What's the next question there? Yeah.
When you get hired, do you get hired before the fact or after the fact that something has happened?
That's a great question. Right.
Yeah.
I think Granddad used to say there's never enough time to do it right, but there's always enough time to do it again. Meaning, yeah, nobody wants to spend this kind of money until you've had a failure. And all of a sudden, the funding for failure investigations is 10 times what the money was for the pre-flight analysis. So I would, as much as I call it a pre-flight analysis, you're right. Everything that you see on here was only funded by something breaking, and the money came down to tell us why it broke and how to prevent it next time.
How can you go and analyze something that has already happened without having the information that I would think? You would need information from onboard sensors, stress gauges, so forth, to give you information
Yeah.
to plug into these equations to say this was your weak link.
Great cap.
But
Yeah.
you need to go out, pick up pieces and try to figure this out.
Yeah, that's a good point. When everything was in the lab, everything's clean and air conditioned, we could have looked at it with a microscope. Now it's all in the dirt, and if you find it at all, you're lucky. Let me skip over that. All right. Yeah, so this is what we get. If you're lucky, you get some Army guys that will go out into the desert and they will scurry, they'll, look through the sand and find the pieces of propellant. They find the busted up nozzle. They find the twisted up nozzle springs and the split open motor case. And then you go to the telemetry guys and they get the radar traces. One rocket went up, you got faster and faster and faster, and then something happened and 3 rockets came down. So we know that was really the warhead going that way. You see, these pieces suddenly lost 300 feet per second. So I think that was the propellant grain and the nozzle getting shot backwards, and then they decelerated with a lower ballistic coefficient. So, yeah, so that's the idea of how do you do a post-mortem when you can hardly get the body.
Yes.
And I think, I hate to say it, that's what keeps us in business, is that we can never do a very good failure analysis after the failure, yet no one wants to do a failure analysis before the failure. So this is how we just limp along decade after decade.
So if you do a pre-flight analysis on this, and it doesn't turn out exactly how you planned it to go,
Yep.
what resources do you have to go back and figure out what? I mean, you cannot. You can be looking at an air-to-surface missile, for example, but you can't, prior to the time that thing is launched, you can't tell if the geometry of the fuel grain has got a flaw in it or anything else before that. You can tell the dynamics of what that thing is supposed to do,
All
and
by
when
theory.
they launch it, by theory.
Right.
And when they launch it, the thing does that.
Yep.
And so
Right.
that's not your fault.
Obviously, we would not have launched it if we thought it was going to do that. So somewhere in our pre-flight analysis, we missed something.
So, but you can't catch that.
Right.
You can't catch a flaw in the fuel.
X-ray and ultrasound are the 2 main methods, of course.
So that,
yeah.
but they give you that option to do that prior to the time you're going to
Yeah.
analyze
In
it.
fact, depending on most, of the high order rockets, it's required. You have to
Yeah.
do a 0-degree shot X-ray at aft, middle, and forward section of the propellant grain. Then you roll the grain, do another shot of X-rays. And you look for voids, you look for unbonds, and then you miss them, and then it blows up, and then in the failure investigation, you call back to the warehouse, you get those X-ray films out, and you start looking to see if you missed that, and then if you don't find the flaw there, you go to the launch tube and you say, oh, here it is, this thing was dropped when they were loading it, and it was, because you can see it had a little dent on the front of it, so that launch tube was, hanging up on the nozzle as it was coming out.
Mhm.
But you're right, it's pretty much, no failures would happen if they would all abide by our theoretical analysis. So it's almost always that the investigation lets us go look for what deviated from theory. And it's kind of the idea of all we can really analyze is the design, and everything after that fails is a deviation from the design. So in other words, you can blame somebody else. Yeah.
On your pre-flight analysis, are you doing, I mean, nothing's perfect, so like the propellant grains,
Right.
do you do analysis of how big a flaw we can have in that grain
Right.
before it becomes a problem, so that when you're doing your quality control, you can say, there's a 1/4-inch thing here that our simulation shows that's okay, or
Yeah.
no, our simulations show that that's going to cause a catastrophic failure.
You got, which propellant grains do you ship to the fleet, and which ones do you let them use for testing or something? Yeah. Yes, specifically on the propellant grains, usually like an 1/8 or a 1/4-inch void is not a big deal.
And you determine that through simulation?
Oh, gotcha. Some people have done that. Usually it's done by test. It's from 50 years ago. The guys that didn't have the fancy software had to just trial and error, and so you got kind of a sense of it from those guys. But now there are guys that'll do the internal ballistics calculations, and they'll actually show the burn getting to that void, and then they show the burn, of course, going into the void and starting to burn longitudinally and radially, and then they show how that void can flatten out without contributing too much more gas into the chamber, because as you know, if you start burning into a crack, that's a lot of surface area, and that starts driving the pressure up, and that drives up the burn rate, which drives the pressure up, which drives up the burn rate, which drives the pressure up, and you go boom. So they generally kind of scale it on the motor. If you're building like on the space shuttle, 12-foot diameter motor, I think they allowed voids, as big as your thumb, because you can burn through that without shocking the system that much. But the other problem is when it gets hot and cold, you cycle it summer, winter, day, night, that little void, if it's got a sharp end to it, can start a crack, and then that crack can become a bigger issue. But I kind of got off onto the, but the main theme of your question was, nothing's perfect, so how do you handle that? The design said it needs to be 2.5 inches, but there's a tolerance, plus or minus 0.010 of an inch. And that's where the statistics comes in. In the 6th degree of freedom software, you can run everything to the maximum material and run everything to the minimum material and do a Monte Carlo in between. You do 1,000 shots, 100,000 shots virtually, and you can create the footprint, all the impact patterns, and so you can kind of report the uncertainty. And that's literally how we would report the munitions. You want to aim at this target. You have to be. You're going to have a lot of scatter, and how accurately you have to aim or how many rockets you have to fire before you can hit a building that is a certain size. That's why they put 19 rockets on one of those launch pods, because you're going to miss with the first 16 and you need a few more. But all right, I don't know how I'm doing on time. I think I'm okay. All right, but yes, so she is going to, the lady in white over there is going to do, she's going to do, zoom in on the statistics of this, and she'll answer a lot more about just the questions you're asking. When you're presented with, the design is this, the guys in the field are saying this, your parts are coming back like this, and you're going to have to put a number on Are we 99% reliable, 99.9% reliable, or 90% reliable? She'll be talking to how you can take the little pinpoint analyses that I do, the little state studies, and she integrates all of that and makes it kind of a holistic mission and a holistic understanding of how you can expect, if you've got a 19-tube launcher, how many of those are going to blow up? How many of those are going to hit the target? How many of those are going to take a weird turn? So she takes it from the small detailed studies into the big picture that you're really asking about. All right. So I think you're next, right? You're 4 o'clock?
Yeah, not here though.
Yeah, so
At 4:30.
you can all follow me to the egret room if you want. We'll go to statistics from here.
Thank you.
Thank you very much. So,